there, thanks for joining me today. Today's topic is something called empirical and molecular formulas, and you probably have already learned how to go from a chemical formula to percent composition. If you're in my class, that was the last thing that we learned. Today we're actually going to go the other way. We're going to start with the percent composition of a compound and work backwards to figuring out the chemical formula. This is actually how we can get mass data in a lab and work backwards to figure out what compound we're looking at. So this is actually very useful for identifying unknown compounds. So again, what do these problems look like? You're going to be given the percent composition of a compound and you're going to figure out the formula based on some percentages. All right, in order to help you learn the process for solving these problems, I have a very simple little rhyme here to help you remember the steps. So it goes percent to mass, mass to mole, divide by least, multiply until whole. And I like to throw in the word sometimes down here. It doesn't rhyme, so I'll put it in parentheses. But we'll say percent to mass, mass to mole, divide by least, multiply until whole sometimes. So that fourth step isn't always required, and I'll show you one example where it is and one example where it isn't. Again, these are simply the steps to solve these problems. And so we're going to look at an example together and walk through all four of these steps. And you'll see that these problems are basically putting together skills that you already know. So here's an example problem. What is the formula of a compound that is 25.9% nitrogen and 74.1% oxygen? So the first step, if you remember from the rhyme, is percent to mass. This is the easiest step involved. You literally get rid of the percentage sign and change it to grams. So it wasn't that easy. Change it to grams. Get rid of that and change it to grams. The way that works is we're basically assuming we have 100 grams. And if you have 100 grams and it's 25.9% nitrogen, you have 25.9 grams of nitrogen. So the way that I show my work on these is I write my grams of my elements over here on the left-hand side of my paper, and then I continue on. And I promise it'll kind of make sense why I put those numbers over there. I'm trying to help you be efficient in your work. So the next step is mass to mole. If you think about stoichiometry, if you have something, some certain number of grams, and you want to convert from grams to moles, you put a 1 on top in front of moles, and you put the molar mass in front of grams. So I want you to think throughout this lesson that to go from mass to mole, you divide by the molar mass. Okay? So I'm not always going to show this full work here. I just want us to remember to go from mass to mole, you divide by the molar mass. So we're going to do that next in this step. I'm going to divide nitrogen and oxygen by their molar mass on the periodic table. So you might want to have out your periodic table, have it handy. Nitrogen is 14.01 and oxygen is 16. Okay? So I'm going to do those divisions and I'm going to write down those numbers as the moles of those elements. So I'm going to switch to my calculator. And for nitrogen, it's 25.9 divided by 14.01. So we have 1.85 or 1.849. Keep a bunch of sig figs on these problems until you get to the very end. So that's moles of nitrogen. And switching back to our calculator for oxygen, 74.1 divided by 16, that's its molar mass on the periodic table, 4.631. 4.631 moles of oxygen. Very good. So that was step 2. So we have done percent to mass, mass to mole. What's next? Next is divide by least. So you're going to look at all of your mole values and you're going to divide all of them by whichever one is smallest. That's what we mean by divide by least. Look at all of your mole values, divide by whichever one is the smallest. So I'm going to divide both of these numbers by whichever one is smallest, which is the 1.849. 1.849. And we're going to get some numbers here. So I hope you don't type this first one in your calculator. It's 1.849 divided by 1.849 gives you 1. Okay. The second one, however, I can't do that in my head. So it's 4.631 divided by 1.849, we get 2.50. So 2.50. Okay, so that one was nitrogen, that one was oxygen. All right, so we have done percent to mass, mass to mole, divide by least, and there's one more step. Multiply until whole, sometimes. So you look at your numbers that you have at this step, and you ask yourself, are these whole numbers? If they are, you stop. And if they're not, you need to multiply the numbers by the same thing so that they will all turn into whole numbers. So what do I need to multiply these numbers by to make sure that they're both whole numbers? The 2.5 needs to be multiplied by 2, so I do the same thing to all of them. So the nitrogen is 1 times 2, so I have 2 nitrogens. The oxygen is 2.5 times 2, which is 5 oxygens. So I did my last step, multiply until whole. So what's the deal? We have 2 nitrogens and 5 oxygens. That's not really your answer. The question was, what is the formula of a compound? So the answer is you need to put that into a chemical formula. So N2O5, 2 nitrogen atoms and 5 oxygen atoms. So that is your answer. So when you go through that process of percent to mass, mass to mole, divide by least, multiply until whole, sometimes, the answers that you get at the end become the subscripts of your chemical formula. Okay? So that was a fairly straightforward example that did use all 4 steps. You did have to multiply until whole at the end. So it was a great example of all the possible steps you would have to do. Okay, let me elaborate just a little bit on that last step, multiply until whole. Notice on the previous one, we got 2.5 oxygens, so we needed to multiply it by 2 to make it a whole number. What you want to look for are numbers that are close to these simple fractions to know that you need to know what you need to multiply by. You want to look for a number that's close to something 0.5. If that's the case, you multiply by 2. If you think back to our calculator, we actually had 2.5045. That's pretty close to 2.5. And we would need to multiply it by 2 to make it pretty close to a whole number. We're going to call 5.009 close enough to a whole number. So if one of your numbers is a 0.5, you need to multiply everything by 2. You would also look for 0.33, which is of course 1/3. You would need to multiply all your numbers by 3 to make them whole numbers. Something close to 0.25 would multiply by 4 to make it whole. 0.2 would multiply by 5 to make it whole. And 0.10 multiply by 10 to make it whole. In a pre-AP level course, these are probably the only numbers that you're going to encounter that you need to multiply by to make them into whole numbers. All right, so let's do another practice problem together. What is the formula of a compound that is 42.9% carbon, 57.1% oxygen? So the first step is percent to mass. So we take the numbers, so 42.9 for carbon, and just put a gram on it. And that's the first step. Oxygen is 57.1%, so we change it to grams of oxygen. So that was the first step, percent to mass. The next step is mass to mole. We want to divide both of them by their own individual molar masses from the periodic table. So carbon's molar mass is 12.01. Oxygen is 16. So we're going to grab our calculator, and carbon is 42.9 divided by 12.01. So 3.572. That is moles of carbon. And oxygen, let's do that calculation. 57.1 divided by 16. 3.569. Moles of oxygen. Okay? So let's think about our rhyme, percent to mass. Mass to mole, we just did that. The next step is divide by least. So I'm going to divide them both by whichever one is the smallest, which is 3.569. divide them both by the same thing. So the bottom one, of course, equals exactly 1. The top number, you can probably guess what's going to happen, but for those of you who need to see it, we take our 3.572 divided by 3.569. So think ahead, what's going to happen? It's pretty much 1, okay? 1.000. So 1.000, close enough, okay? So that is your carbon and that is your oxygen. The final step is multiply until whole sometimes. This is a prime example of you don't always have to multiply until whole. These are already whole numbers, so you stop. So you have 1 carbon, 1 oxygen. That's your chemical formula, CO. The name is carbon monoxide. So that's another straightforward example and a good example of not always having to do the final step, multiply until whole. We did not have to do that in this problem. All right, so far what we've calculated is the simple empirical formula. The empirical formula is the most reduced version of a chemical, okay? So for instance, if you had hydrogen peroxide, which is H2O2, if you went through this process and calculated the empirical formula, you would actually only get HO, which is the same ratio. It's a 1-to-1 ratio, but it's not the true molecule. H2O2 is the true molecule, okay? Another example is the chemical benzene, which is C6H6. If you went through the process that we just talked about, percent to mass, mass to mole, divide by least, multiply until whole, you would actually just get CH, which is actually the right ratio, but it's not the true molecule. The molecule of benzene is C6H6. So these over here, the simple versions are called the empirical formula. I'll call it EF, okay? Whereas these over here on the left-hand side, which is what the molecule actually looks like, these are called the molecular formula, and these might be different. So again, here's an example. Hydrogen peroxide, the lowest ratio is HO, but the actual formula is H2O2. Can y'all whisper? Shh. Can y'all whisper? That's okay. Shh. Whisper. If possible, we always want to give the molecular formula. It is more descriptive of what the molecule actually is. And to do this, you need one more piece of data. You need to know the molar mass of the compound. So how do we use that? Okay, you take the true molar mass, which is given in the problem or solved for in the lab. You divide that by the empirical formula's molar mass to get an integer. And you might need to round it off. You know, it might be like 5.99 and you round that to 6. And then you would multiply the subscripts of the empirical formula by that integer to get the true molecular formula. It's worth noting that ionic compounds don't ever have a molecular formula, since the definition of a formula of an ionic compound already is the lowest possible ratio. You'll only ever see molecular or covalent compounds having a molecular formula. It's just a little side note for those of you who like to kind of think above the level of where I'm teaching. All right, so here's the sample problem. What are the empirical and molecular formulas for a compound that is 92.3% carbon and 7.7% hydrogen? The molar mass of the compound is 78.110. Okay? Now, calculations show if you go through the process of percent to mass, mass to mole, divide by least, multiply till whole, that the empirical formula is CH. So the ratio of carbon to hydrogen has to be a 1-to-1 ratio. That's what the empirical formula tells us. But does the molar mass match the molar mass given in the problem? 1 carbon and 1 hydrogen. If we go to our calculator and add it up, 12.01 for 1 carbon plus 1.008 for 1 hydrogen, the molar mass of CH is 13.018. So I'm going to write that down over here. This is 13.018. Okay? That does not match the 78.110 given in the problem. Okay? So we're going to remember that we divide the true molar mass, which is always going to be the bigger number, by the empirical formula's molar mass to get an integer. So I'm going to divide, I'll do it up here, 78.110 divided by 13.018. And this should give me something very close to an integer. So let's go to our calculator. 78.110 divided by 13.018. Let's do the answer. 6.000. You always want to round that to the nearest possible integer, so we're just going to call it 6. Okay? And then we take that number and we multiply the empirical formula by that value. So that 1-to-1 ratio, I'm going to multiply it by 6, so it becomes a 6-to-6 ratio. So my molecular formula is C6H6. So it's actually that benzene compound that I mentioned earlier. Okay, we're going to do a couple more problems together here to practice this concept. The percent composition of caffeine, which is one of my favorite compounds ever, is 49.5% carbon, 5.2 hydrogen, 16.5 oxygen, 28.9 nitrogen. What is the molecular formula if the molar mass of caffeine is 194.1 grams? So you still begin these problems by doing the rhyme. Percent to mass, mass to mole, divide by least, multiply to a whole. So let's begin by listing our listing our elements over here on the left-hand side and changing the percents to grams. So 49.5 grams of carbon, 5.20 grams of hydrogen, 16.5 grams of oxygen, and 28.9 grams of nitrogen. So that was step 1, percent to mass. Next is mass to mole. I divide each element by its unique molar mass. So carbon is 12.01, hydrogen is 1.008, oxygen is 16, and nitrogen is 14.01. These are just the molar masses from the periodic table. This is going to convert from mass to mole. So I'm going to get my calculator and do some number crunching. So carbon is our first one, 49.5. 49.5 divided by 12.01. 4.122 moles of carbon. Next, hydrogen, 5.2 divided by 1.008. It's going to be close to 5. Let's make sure we get 1.008. 5.159 moles of hydrogen. It's important to keep track of which row is which element. Oxygen is 16.5 divided by 16. 1.031 moles of oxygen. And nitrogen is 28.9 divided by 14.01. 2.063. All right, and that's moles of nitrogen. So let's go back to the rhyme. Percent to mass, mass to mole, just did that. Divide by least. So in this step, you divide all the numbers by whichever one is the smallest. So the smallest one is here, oxygen, 1.031. 0.031, all of them. So oxygen, of course, ends up being 1. Let's see. Carbon is 4.122 divided by 1.031. 3.998. That is close enough to call it 4. Next, hydrogen, 5.159 divided by 1.031. Let's see, 5.00, let's call that 5. That's close enough. Call it 5. And finally, nitrogen, the last one, 2.063 divided by 1.031 is 2.000. We're going to call it 2. Okay? So go back to the rhyme. Percent to mass, done. Mass to mole, done. Divide by least, done. Multiply until whole sometimes. Do we need to multiply these numbers to make them whole? We do not. They are already whole numbers. So just keep track of which is which, and that becomes your chemical formula. So it is C4 H5O N. So this, that should be a big N. Okay, so this is called the empirical formula. Okay. The question, though, asked for the molecular formula, and it told us that the molar mass of caffeine is 194.1. So we just need to ask ourselves, is the molar mass of this 194.1, or do we need to multiply it by something to get it to the right molar mass? So I'm going to go to my calculator, and I'm going to add up 4 carbons, 5 hydrogens, 1 oxygen. Oh, I'm sorry, that should be a 2 on the nitrogen. Okay? So let's add it all up and see what we get. So 4 times 12.01 for carbon, plus 5 times 1.008 for hydrogen, plus 16 for oxygen, plus 2 times 14.01 for nitrogen. We get 97.1. That does not look like a match to me. Okay, so you need to think, what do I need to multiply by to get it to equal the 194.1? Well, if you do 194.1 over 97.1, remember that was my rule for how to figure out what that integer is, you get a 2. Now some of you could probably have just looked at that and seen, oh, I need to multiply by 2. That's fine. If you need to do the dividing, go for it, you get a 2. So that tells us that our molecular formula is double the empirical formula. So we're going to double it, and it becomes C8, H10, O2, N4. And that is our final answer right there. That is the chemical formula of caffeine. Okay? We are going to do one more practice problem together. All right, so ascorbic acid, which is vitamin C, it's the kind of sour taste in citrus fruits, is 40.92% carbon, 4.58% hydrogen, and 54.5% oxygen. We want to know the empirical formula of ascorbic acid. Okay, so this one's actually just going back to empirical formulas. It's not one of these with the extra step for molecular, but it's still good practice. So we do 40.92 grams of carbon, 4.58 grams of hydrogen, and 54.50 grams of oxygen. So percent to mass, done. Mass to mole is next. So you divide each one by its molar mass. Carbon is 12.01, hydrogen is 1.008, oxygen is 16. So let's grab our calculator and crunch the numbers. Carbon is 40.92 divided by 12.01. Let's see what we get. 3.407. That is moles of carbon. Hydrogen is 4.58 divided by 1.008. 4.544. That's moles of hydrogen. And oxygen is 54.5 divided by 16. 3.406 moles of oxygen. Okay, so go back to your rhyme. Always go back to the rhyme. Percent to mass, done. Mass to mole, done. Divide by least. So divide all of these numbers by whichever one is the smallest. The smallest is 3.406. So I divide them all by that same number. Now, the first and the third one here, you can probably see equal pretty close to 0, or sorry, close to 1. But let's check out the one in the middle. 4.544 divided by 3.406. We get 1.334. So that was carbon, hydrogen, and oxygen. So go back to your rhyme, percent to mass, mass to mole, divide by least, multiply till whole, sometimes. This is one of those sometimes. These numbers right here are not all whole numbers, so you need to multiply them all by the same thing until they are whole numbers. So you need to think back to those fractions that I told you to look for. Okay, so do we see one of those? Let's see. Do we see one of these fractional numbers here? We do. We had a 0.33, so we're going to multiply by 3. All of them get multiplied by 3 to make it into a whole number. So times 3, 3, 3. So carbon becomes 1 times 3, 3. Hydrogen is 1.33 times 3, which you can use calculator if you need to, but that equals 4. So H4. And then oxygen is 1 times 3. So oxygen is 3. So that's it. That is the empirical formula of ascorbic acid. So that's all. I hope it was helpful. If you have any questions, feel free to leave a comment or ask your teacher. Thanks for watching.